Thanks. So a theme of CS51 that we're going to see throughout is abstraction. What do I mean by abstraction? I mean taking detail and hiding it so that we don't have to think about it. In our first lecture, Dr. Leitner talked to you about the sizes of some programs. Our only hope of understanding really complex programs, big programs, is by not thinking about the whole thing at once. And so the way we do that is we take parts of them and hide their complexity and give us sort of a simple way of looking at them. That's abstraction. So today, that's what the lecture is going to be about. It's going to be about a particular kind of abstraction, procedural abstraction. And then we might also get to another kind. So I'm going to start writing some code here. And then we'll see what happens. So you guys have probably written a bunch of these functions by now to the point where they're not that interesting. But this is how we're going to start. So if you have a list of ints and you want to increment every int in the list, you might write a function like this. So you take an int list, you return an int list, and then we're going to do our usual structural decomposition of the list. If we increment the empty list, we get the empty list. Here we have the first element of the list, and we have incremented the rest of the list. And of course, what we want to do is add 1 to the first element of the list and cons that onto the rest. All right, very good. We've written a function to increment every integer in a list of integers. Now, suppose we find out that we also need a function to, whoa, okay. There we go. Suppose we also need a function to decrement every int in a list. Well, we could start writing it from scratch, or we could notice that we have something similar. So we'll just copy and paste this here, change the comment there, change that there. I guess we need to subtract 1 here, and okay. So that's fine. Shh. I know what you're talking about. Let's leave it for now. Okay. All right, and then we find out, well, we also have to be able to add 6 to every int. Ooh. In a list. So, well, we'll copy this again. We could call this, I don't know, add 6 list, and then we need to make sure that we add 6. And we need to make sure that we recur with the right function. That's great. We now have these 3 functions that increment all the ints in a list, decrement them, or add 6 to them. And you might be noticing this is silly. So let's at least try them out and make sure they work. I'm going to hit Control-C, Control-B, and that should run everything in the buffer. There we go. And now we could try them. So let's say we want to try inc list on a list 2, 3, 4. Well, that's interesting. It looks like we have a bug, as one of you pointed out, in inc list. So we'll go back here and we look at it. I notice that it's looping until it blows the stack, and I think that's probably because I'm recurring on the same list. So we need to add a prime there. That's good. We'll send that down there again. See if inc list works now. It does. All right, we also want to be able to use dec list. Damn. So it looks like we have a problem with dec list. I think we need a prime there. All right, we fixed that. And of course, we have to fix it here too. So not only did I write these 3 functions, now you have to deal with the names of the 3 functions, remember the 3 functions, document the 3 functions. But when I had a bug in one of them, because I copied and pasted, I had a bug in 3 places. And I had to go fix it in all 3 places. So what we might do is we might look at this and say, there's a common pattern here, and instead of writing this similar thing 3 times with slight differences, we can abstract. We can take the differences and turn those into a parameter. So what do I mean by that? I mean, in this case, all of these add an integer to a list of integers, where decrement adds -1. So we could write that function instead. We could say let rec add to list. Now, let's actually start by copying the thing that we want to abstract. And say what we want to do now. Add an int to every int in a list. So if we look at these things, we see here we're adding 1, here we're adding 6, here we're adding -1. So clearly that's what we need the parameter to be. That is, we need some parameter n here. And so to find out what that is, we'll make it a parameter here. We have to make sure we pass it along here. And then let's rename our function. All right, so we just successfully abstracted. We found a common pattern, and we made something new that encapsulates that pattern so that we don't have to write it again. And we only have sort of one thing to remember, one thing to deal with, one thing to debug. And then, if we need IncList, we can say, well, let IncList x's equals add to list 1 x's. And let dec list x's equals add to list -1 x's. And let add 6 list x's is add to list 6 x's. Now probably we wouldn't even go to the trouble to define each of these because anytime we want to increment a list now, we could use add to list directly. But just to make sure, let's try them now. So our new version of dec list works. Add 6 list works. Great. Now, there's something else I'm going to point out to you here, and we're going to understand a little bit later why it works, but it just lets us save a little bit of typing. Here I'm saying to increment the list x's, I'm going to add to the list 1 to x's. It turns out I can also just say to increment a list, I need to add to the list 1. So the reason for that is that add to list 1 is a function that you know what? We'll get to this in a bit. I apologize. All right, so we're good. We made our abstraction. Now we find out, yes, question in the back.
Have you actually tested your new functions? Shouldn't you be putting in 2 arguments?
Sorry?
For add 6 list and dec list? Or,
If I were,
sorry, never mind.
I'm skipping the test at this point in the lecture because we have a lot to get through. Okay, so now we find that we need another function. We need to square every int in a list. And it turns out that squaring every int in a list can't be done by adding some constant to every int in the list. Square every int in a list. So again, we have a list of ints. We're going to return a list of ints, but we need to write this from scratch, it looks like. There was some confusion as to what the prime means on x's prime. It's just part of the variable name. OCaml lets you put apostrophes in variable names. So it doesn't mean anything to OCaml, it's just a convention that I'm using. So we need to square x and cons that onto squaring the rest of the list. Let rec square list 2, 3, 4. That looks good. Okay. So this is annoying because if we look at square list and we look at add to list, they still look very similar, right? The only thing that's different between square list and add to list is what we're doing to x. Here, we're adding n to x, and here, we're multiplying x by itself. In fact, if we wanted to, we could make it really clear what's going on here. As follows. We could say, well, add n. Oop, I think this locked up. There we go. All right, back to where we were. So we look at square list, we look at add to list, or inc list, and what we might notice is that the only difference is what we're doing to x. So just as before, when we abstracted out what integer we're adding to x, we can abstract out the operation that we perform on x. So in each case, x is an int, we're performing some operation to get a different int, so that is to say we can abstract out the int-to-int operation. So again, I'm going to start with the thing I'm abstracting and pull out the part that I want to be different. So that is to say that instead of squaring x all the time, I want to apply some function f to x that's going to differ each time. And I'm going to make that function a parameter. And because that is a function that tells us what to do to an int to get another int, its type is int arrow int. So this function that we've written here, which I'm going to change the name of in a moment, takes an int arrow int function and applies it to every element of a list. So we have to make sure we pass that along there. And what does this do? It maps a function over every element of a list, of an int list. And so in fact, that word map, that's what the name of this function is going to be. So you can see here now this function map takes an int arrow int function, an int list, and an int list. So let's see how to use this new abstraction. What are some of the functions that we want to apply over a list? Well, we had to do things like we had to increment everything in a list. So we can say inc x equals x plus 1. We also need things like add 6, x equals x plus 6, and square x equals x times x. So these are all int-to-int operations on x that we might want to map over a list. And so what that means is now we can rewrite our functions like, for example, inc list well, we don't need to do the recursion at all. We can just say that we want to map inc over the list. Any questions about that? Yes?
So when you have at colon int arrow int, so I have to explain that. But that's essentially saying f is going to be a function. That's the way to identify whether.
Yes. The question is when you have f colon int arrow int, is that a way to say that f is a function? Yes. Arrow means that you have a function and the thing before the arrow is the type of its argument and the thing after is the type of its result. Yes. So we can write inc list. We can now write, add 6 list is map add 6 over the list. We can write square list as map square over the list. And of course, these things work. So we've now seen how to abstract over an operation instead of just over an integer. Do we have any questions? Okay, so I was able to rewrite inc list and add 6 list and square list, but there's a trickier case. What if we actually want to write this function that we wrote before, add to list? So you notice here, add to list takes an int n to add to every element of the list, which means that we can't predefine the function. We can't say add, well, if we say add n, that needs to take another parameter, n. I don't know. Yeah, maybe. Okay, so we need to kill Emacs again. Okay, so if we want to write add to list, we have a problem. So we start trying to write this. It takes the n int that we want to add to the list, and the list that we want to add to, and then we want to say map. Well, we want to map something over the list, but what we want to map is a function that adds n. And we can't out here write that function because we don't know what n is. So what we need to do is write the function in here. So I can say let add n x equals x plus n in. So I just defined a function locally. We've seen how, I'll take a question in just a moment. We've seen how you can define other kinds of variables locally. You can also define functions locally. And now I will take your question.
Couldn't you just define the function out and then put it inside the, like a call to the function inside the new function afterwards?
So the question is, couldn't I just define the function outside? And
Yeah, add n.
right. So for example, are you asking whether I could take this definition of add n and put it up here?
Yeah.
All right. So I can try to do that, but when I try to send that to OCaml, do you have an idea what's going to happen? Anyone? Yeah. It's going to say, I don't know what n is. Unbound value n. Because right here, n hasn't been a parameter to a function. It hasn't been bound anywhere. And so it doesn't have any meaning. N only has meaning once we're in here where we can see this parameter n, which is different for different calls to the function. So if we want to do this in map, we have to define somehow a function inside this other function. And we can do that. Now it works. We can try it. Add to list 8, 2, 3, 4. It works. And so we might look at that and say, well, sure, that works, but it's a little inconvenient. Because we just defined this tiny function here, and we actually used, we had to come up with a name for it. We can do this in a slightly more convenient way. And let me show you what that looks like. So the first thing I'm going to point out is you can take your lets and you can put them anywhere. So for example, I could say map. I just did a little transformation there. I'm saying the function that I want to map is that add-n function, which I'm defining right there in place. Does that make sense to everyone? Do you have a question? Yes?
How's that word named?
I haven't gotten there yet. I'm working my way over to something that's going to save you a little bit of trouble. So what the next thing is this. If you have a function, a small function, that you just want to use once, and it's so small that it's not even worth thinking up a name for it, you really just want to write down what you want to do and keep moving. In OCaml, you can write down a function as a value, as opposed to defining it using let. And so the way you do that is you use the keyword fun, you write the parameter, an arrow, and the result. So what I've said here is I want a function of a parameter x whose result is x plus n. So that's an anonymous function. You'll also hear it called a closure. You might hear it called a lambda, and that's because in in the theory behind this that people do, they write a lambda for fun, possibly due to a typographical error for someone who was using carets in the 30s. So there we go. We have add to list, and that works. So it turns out all these functions that we wrote up here, where we defined inc and addx and square, we didn't need to do that. We could define inc list as map. We have a function that takes x and adds 1 to it. We want to map that over the list. And we can define add6 list as we'll map. We'll write a function that takes x and add 6 to it. And we can do the same thing. Square list. We can write the function that takes a parameter x and squares it. I want to point something out to you here, which is it doesn't matter what we call the parameter. I mean, it matters for humans reading it. It doesn't matter to OCaml. So if I didn't want to call this x, if I wanted to call it y, that's fine as long as I rename it consistently. If I wanted to call it that, that's fine as long as I rename it consistently. Did I get that consistent? Yes. Great. This line's probably too long. Yeah. Any questions? Yes.
So this map function seems pretty useful.
Yes.
It does.
Yes, the map function is very useful.
Anyway, I know you programmed the hardcode up there. Is something that actually just exists that we could...
It is in the library. It's a little bit different in the library, and I've seen about 6 questions on Piazza about how it's different in the library, and so I'm going to show you guys today how to use it, if you haven't figured it out already. Any other questions? So yeah, map is a really useful function. It's actually, it's so useful that, how many of you have heard of MapReduce? A good 25% of you. So MapReduce is Google's framework for doing large amounts of computation distributed onto a bunch of different computers or cores. And so the great thing about map, which is the first step of this, is you're doing something to every element in a list, but there's no interactions between them. If I add 3 to every element in a million-long list, I don't have to do that in order. I can split it up into chunks and do them all. So that's another part of the power of map. And it's really, really common to have a collection of things and want to do the same thing to everything in the collection. Question?
If I wanted to include a variable in 2 functions, how would I write the end statement?
If I wanted to put a variable in 2 functions, how would I write the in statement? Are you asking, like, you want to write a helper that's accessible from 2 different places? All right, if you want to write a helper that's accessible from multiple top-level functions, then you have to define it at top level as well. So you don't get to use an in. Yeah. You don't, well, so each one of these top-level definitions doesn't have an in. We only use in when you're trying to define something locally inside an expression. And if you're defining 2 functions where you want to use the same thing locally in both, then you can't use let in to define it there. Okay. Any other questions? Okay. So there's an interesting thing happening here that we can understand now that we've seen fun, which is, you might wonder, how do I use fun to write a 2-argument function? So, for example, suppose I want to write a function to square an int and add it to another int. Sure. So we want to write let square and add. And we could call them, x int and y int. And we'd say that's x times x plus y. That works perfectly well. Well, it turns out that what we've written here with these parameters, this is actually syntactic sugar. That is, it's a prettier way of writing a more fundamental thing that's happening. And that more fundamental thing is that fun is how functions are made. So we could write this as square and add is a function that takes x and returns a function that takes y and returns x times x plus y. And we could actually put a type annotation on that whole thing there. So what this is called is that functions in OCaml are curried. What that means is if you want to take multiple parameters, they don't actually have multiple parameters. Every function in OCaml has one parameter and one result. So we fake multiple parameters by writing a function that takes one parameter and returns another function that takes the next parameter. Does that make sense? Any questions? So what that means is that when we look at this type here, int, arrow, int, well, the way that that actually associates is like this. That is, this is the type of a function that takes an int and returns a function that takes an int and returns an int. And OCaml knows that arrows associate to the right because that's what you want most of the time. So you don't need to write the parentheses. So what that also means is that we can partially apply functions. So, so what do I mean by this? Well, suppose that we're really interested in adding 9 to a bunch of numbers, but we don't know that. We just know that we want to add 3 squared. I'm sorry if this is getting contrived. It'll get less contrived again in a moment. So we could take this function square and add, pass it 3. Add 9 is square and add 3. Well, what does square and add 3 do? It returns the function that takes another int and adds 3 squared to it. So we can admit this definition, and you can see here, add 9 is an int arrow int function. So let me give you some nicer examples of this. You saw a little earlier that we defined inc list of some list x's. Did this really just lock up again? Okay. It's easy to fix.
What did you just press to load everything?
To load everything in the buffer, I hit Control-C, Control-B for buffer. Yes.
Is that even the bottom part?
Sorry?
The part where you input stuff that you got.
Mm-hmm.
So they're like two halves, right?
Yes.
Top and bottom half. Like the bottom half, and then I also got that.
Yeah, Control-C, Control-V will open.
Oh, I actually have, yeah, Control-C, Control-B will open that. I actually have a key combination set up, though, that makes the font bigger and starts UTOP and adjusts the windows to how I want them. So that's how that started. Okay, so we saw before that we might write inc list. Like this. By the way, when you write one of these fun things, or I'm going to call them lambdas actually, you can put type annotations on them, but usually you want them to be small enough that you don't really need that. I would suggest not writing anonymous functions that take up more than a line for now, maybe 2 lines. If it's more complicated than that, it's probably a good idea to give it a name. Okay, so looking at this, what you can see is that we're defining inc list of some list x's to map some function over x's. But really what we're saying here then is map takes a function and gives us back the function that does the mapping. So this is the function that does the mapping. So because functions in OCaml are curried, we can partially apply map. We can give it the thing we want to map, and that gives us back the function that does the mapping. If we want to, we should probably write down the type here. Might be a good idea. So that's gotten fairly compact. One more thing that might interest us, though. Let's look at, try to understand the nature of plus a little bit better. So actually, I'm just going to go down to utop here. So plus, that's our addition operator. If we type it by itself, we're going to get a parse error. But every operator in OCaml is actually an ordinary function that's just spelled with punctuation. And the way you get it to act like an ordinary function is you write it in parentheses. So if we write plus in parentheses, then we can actually get our hands on the value that's the plus function. And we can see that that's a curried int arrow int function. So we can use it to add some ints. We can also use it to, well, we can partially apply it. So we can say plus 3. Well, that gives us back the int arrow int function that adds 3. So, we could have written inc as let inc give me the function that adds 1. Question?
Yeah, can we go back and ask a question about let inc underscore list colon and list that line? So how come you were able to get rid of the x's at the end?
How was I able to get rid of the x's at the end is the question. So the way I was able to get rid of the x's at the end was I noticed, let me actually just bring this back for a moment. Let's write it like this without the types. It'll make it a little bit clearer. So I noticed that this says to increment the list x's, we're going to map that function over x's. So that is that we have a function that when we apply it is then going to pass the increment function and x's to map. What we could do instead is call map on the increment function. Actually, let me do a step in between here. So because things are curried, what we're actually saying here is that inc list of x's is map applied to this increment function that gives us back a function that then increments x's. So another way to say this is that increment list is the function that increments a list. Does that help at all?
Yeah.
Okay, yes. So, okay. And we can do the same thing for deck list. And so on. So going back to what I was showing you a moment ago, because plus is a curried function, we can partially apply plus to get the function that does that addition. Question?
How does the plus become an infix rather than a prefix function?
So the rule in OCaml is things that are written with punctuation, operators, are infix.
Okay.
Things written with letters and numbers and apostrophes and underscores are prefix. I believe there's an exception, which is mod is infix.
Okay.
I don't know that there are any other. Yes.
Can you explain what those terms mean?
What do prefix and infix mean? Prefix means, for example, like this function int list, we write it in front of its argument. So it's prefix. Whereas plus, we usually write between its arguments, so it's infix. That's what that means. Some languages also have postfix operators. OCaml doesn't, but type constructors in OCaml are postfix. So for example, if you want to say that you have a list of ints, you write int list. List is like an operator on int that you write afterward. Okay. Does that answer your question? Okay. So we can make plus prefix, meaning we write it first, and that means then that we can partially apply it. Which means that what we want here really is we just want to map the function that adds 1. And so for deck list, we want to map the function that subtracts 1, right? Shall we try this? Deck list 2, 3, 4. Well, that's surprising. I don't think that I decremented those by 1. Can anyone see what's happening?
It's doing it 3 times because there's 3 elements.
Well, I mean, yeah, I'm doing the same thing to every element of the list, but can you see what I'm doing to every element of the list? Yes?
We're decrementing it by larger than
You could say that, yes. Yes. So to make it really clear what's going on here, when I partially apply minus, 1 is the first argument to minus, not the second one. So that is to say, this is like saying, I want the function that takes some x and does minus 1x. Which if we skip that, if we switch that to infix, that's not the function we wanted to map. That is the function we were mapping. The function we want to map is x minus 1. So be careful with your order of arguments if the thing that you want to partially apply isn't commutative. This turns out to be fairly confusing with things like, say, less than. So if I want to partially apply less than 3, you might think that this is the function that tells me if something is less than 3, but it's really not. It's the function that tells me if something's greater than 3, because 3 is the left argument to less than. So be careful. Any questions before we move on? Yes?
Is there any way to only use the second argument from something if you have to, make a new function?
That's a good question. Is there a way, the question is there a way to only use the second argument? So I'm going to rephrase your question as, is there a way to just partially apply to the second argument? And the answer is not built in, but we can write it. So I'm going to write this now. I wasn't planning to do this, but we might as well. What we can do is we can write a function that takes any two-argument function and switches the order of their arguments, of its arguments. So I'm going to call this function flip. And I'm not going to write down its type for now because its type is a little complicated. But we could say flip takes some function f and some arguments y, x and y, and applies f to y and x. So that is to exchange the order of the arguments of a function. We could be more precise there. So using that, then we could say dec list equals map flip minus 1. So flip is taking minus, exchanging the order of its arguments, and then we're providing 1 as the second argument. So yeah, you can do that. And if we try it, of course, we also could have just said dec list is map plus minus 1. Okay, and similarly now we can say let add to list, which takes some int n, is map plus n. So what you can see here is it's almost like OCaml is writing some code for you. You no longer have to write the function that adds n. You partially apply, and it gives you back the function that does what you want. Question?
So does map basically just get a function and then apply to the entire list, give it a parameter, this, and then do that to the list?
Is map basically a function that takes a function, applies it to the entire list? Yes. Yes. All right. And with that, let's take a 5-minute break.
You like this shirt?
Oh, sorry, I should pause my recording. Please take your seats. Everyone, please take your seats. We need to continue. Thank you. All right. So I've introduced you to one higher order function, map. What does it mean to say that it's higher order? it means that it's a function that operates on functions. And so you could actually sort of count a function that operates on functions is a second order function, but if the function it operates on also operates on functions, you have a third order function, and so on. We'll just say higher order so we don't have to count. Let's try another one. And so to get there, I want to look at a different pattern. And this is another pattern that you've probably seen a few times in your homework. Suppose we want to add up the ints in a list. Well, we know how to do that. Let's call it sum. We'll take a list of ints. Okay, I think we crashed again. Right. To add up the ints in a list, It's interesting that it's locking up in the same place. Okay. And that I make the same typo every time. Okay, we got further this time. Right, so we want to add up an int list and get an int. So we're going to follow the structure of the list as we do much of the time. Match x's with our possibilities are the empty list, or we have the first of the list, and we have recursion on the rest of the list. So then we think about this and we say, well, for the empty list, the answer is 0. Why is that? Because plus is a unit for addition. And if we have the sum for the rest of the list and the first of the list, we just have to add that on there to get the sum of the whole list. So we can send that definition down there. We can try it on my favorite list. We get 9. Beautiful. Now, suppose that we need to multiply the ints in a list. To multiply the ints in a list, well, we might get really tired of doing recursion on lists, so we're going to be bad and copy and paste again. And then rename some things. And I've got us now back to the template for processing lists. So I can look at this again and fill it in. I can say the product of an empty list should be 1. It's usually what an empty product is. And if we have the product of the rest of the list and we have the first of the list, then we multiply them to get the product of the whole list. So here we have a pattern. We have two functions that follow a similar pattern, but neither of them falls into the pattern of map. There's something slightly different going on here. And one thing that might clue you into that is map always, you end up taking a list and giving back a list, and here we're taking a list and giving back something else. In this case, an int, not a list. So let's try to abstract here, figure out what the common thing is, and write a new function. So I'm going to, as I usually when I abstract, I'm going to copy, paste, and then modify. So I need to look at these two things and say what's different. Well, one thing that's different is sum has a 0 here and prod has a 1 here. So I'm going to make that a parameter. I'm going to call it, I don't know, z for 0. And that is an int, I believe. So I need to add that here. And then the other thing that's different is that sum is adding x and the result for the rest, whereas product is multiplying. So I need to abstract that function to say what I want to do to combine these. So that function in both cases is an int arrow int function. That's what plus is, that's what times is. So let's take a function, f, which is an int arrow int function. And of course we need to pass that along here. And now let's give this a name. I'm just going to tell you what its name is going to be. And then we'll have to figure out how to describe it. Its name is fold right. And that might suggest to you that there's also a fold left, and there is. So why do we call this fold? We're sort of taking a list, and one con cell at a time, we're folding it up into some other sort of value. And the reason why we're calling it fold right is it's going to kind of work from right to left. And the way you can see that is that in each case, when we recur on the rest of the list, and then do the operation for the head of the list after that. You follow? So, in fact, the best thing I can say to describe this here is to fold a function over a list right associatively. And so using that, I can rewrite sum and product in more compact ways. In fact, I can write a lot of functions with this. So let's try that. Let's think about, well, how do we write sum? Let sum equals, I know I want to write it using fold right. Sum takes a list of x's. And I know that the first parameter to fold right is f. And for sum, f was addition. So I want to pass addition as my operation. And then the next argument to fold right is z, possibly for 0, because where we have z here, in sum, we had 0. So we want the second argument to be 0, and then we give it the list. And so that, we need to add fold right there. So now we have a version of sum written with fold. Any questions? Yes.
Why is sum an int to int?
Why is sum an int to, sorry, can you say that again?
Why is sum an int to int?
Sum is not an int to int function. Sum is an int list to int function. Are you asking about, you're asking why is plus an int to int function? Plus is an int to int function because it needs to take an int and return a function that takes another int and then returns an int. Okay. And yes? Yes. Let's go, yeah.
Can you get rid of the x's again?
Yes, we can get rid of the x's. The question was, can we get rid of the x's as we did before? And yes. Instead of saying the sum of a list is folding right plus with unit 0 over the list, we can say summing is folding right with plus and 0. Yes. Question over here somewhere. Or is that question gone now? Okay. Any other questions? Yes.
Is sum still defined in terms of int list to an int?
That's a good question. I didn't write a type here. Yeah, the type of sum is still int list to int.
Even though we remove the x's as a...
Yes, even though we remove the x's, because you'll notice that the type of fold right takes a function and an int and gives us back an int list to int function. So since we're applying fold right to a function and an int, then it gives us back an int list to int function. Yes?
Could you talk again about getting rid of the x's and what that means?
Could I talk again about getting rid of the x's and what that means? So in particular, what does it mean when I get rid of these x's here? Yes? I think, so, trying to think of a different way to explain this. Can I take the other question and then come back to this? Yes. Yours was the same question. How many people have that question? Okay, then we should answer that question. So the reason you can get rid of x's is because we're doing a partial application. So just like we can, if we want to say we want the function that adds 1, the inc function. We can say inc of x is plus 1 of x. I just use plus in prefix form. But you'll recall plus is a function that takes an int and gives back an int to int function. So if we just write plus 1, that is the int to int function that we want. So we need to make sure that we also don't take a parameter over here. So inc is the int to int function that we get from applying plus to 1. Does that clarify it at all?
So it already like takes the place of the other function that x previously.
I don't understand that. Yes.
So then if I had plus 1.0, would it be like float to float?
Question is, if I had plus 1.0, would it be float to float? Let's try it. Well, that's going to be a type error because plus wants an int. But if I use plus dot 1.0,
Something like let n equals plus 1.0.
let inc equals plus 1.0. So that's going to be a type error because plus is for adding ints. But if we want to use plus dot, then yes, let's call that inc f for floats. Then yes, we can say inc f is a float to float function. So anytime you have an OCaml function that takes multiple parameters, which are curried, you can apply it to just some of them and get the rest of the function back. Yes?
Read in English, starting from x const x prime yields f of x. Could you read that in English what that's doing?
So the question is to read this line of fold right in English?
Yes.
Okay. So what we're saying, I'm going to start at the top of the function then. Fold right is a function that takes an int to int to int function. You can think of this as a binary operation on ints. An operation that takes 2 ints and gives you an int back, like plus or times or just keep the first one or whatever. Z is an int, and what we want z to be is the answer for the empty list. That's what z is about. And then x is a list. And we're going to recur through this list. When we see the empty list, our answer is z. So if we're summing, then we want it to be 0. If we're taking a product, we want z to be 1. And then here, when we have a list where we have the head of the list x and the rest of the list x is prime, what we want to do is we want to fold up the rest of the list x is prime using the same f and the same z. And then we want to take that result and we want to combine it with x using f. So in the case where f is plus, what we're saying is fold up the rest of the list, which in this case is going to sum it, and then add x onto that. In the case where we're doing a product, then f is going to be multiplying x by the product of the rest of the list. Does that help?
Yes, so that's this, to clarify, that's the second argument of f.
Yes, x is the first argument of f, and the result of the recursion is the second argument of f. Do we have any other questions? Yes?
If you wanted to do like, what if you didn't have commutative, I think this word commutative function for f, and you wanted to have x be applied after?
If you just want f to be flipped, you can use flip.
Okay.
Right? You can write the function that's f with its arguments reversed. If you want to take the list and you want to start at the beginning and sort of accumulate from the left instead of accumulating from the right, then that's what fold left is for. But I'm not going to show you fold left today.
Okay,
Sorry?
because it's really, really hard, right?
No, it's not really, really hard. I just have other things I have to get to. Okay. So that you can do problem set 2, essentially. So if you're confused by this chopping off x's thing, you never have to do it. But generally, what you can say is the rule is if you have a function, f with some arguments, and it's defined to be g with some other arguments, and the last ones are the same, then you can get rid of them. That's what's going on there. Let's not actually worry about it too much. I think when you get an intuition for higher order functions, that will make sense as well. All right. So we've written fold right. It works. It takes lists of ints and uses a right associative operation on ints to collapse it down to one int. But what if we wanted to do something different? For example, suppose we wanted to convert a list of ints to a list of strings. So I have a list of ints, and I want to get back the list of all of those ints as strings. So that sounds, I can write that function, let rec ints of strings, x's is an int list, and we want to return a string list. I named this function wrong. So we can write that function, and it looks a lot like the things we've been seeing throughout this lecture, but map, as we wrote it, isn't going to help us with this. Right? Because the map that we wrote, let's find that. The map that we wrote is just for mapping ints to ints. And here we have a function where we want to do something to every element of a list, but we're going from ints to strings. So, we could write another map for int to int string functions and another map for, string to pair of float and character functions. We could write a bunch of different versions of map, but of course we don't want to do that. So instead, what we want to do is make map polymorphic, because there's nothing about the way that we wrote map that requires it to operate on ints, other than that we said so. Yes?
How does it work if it's let rec strings underscore of ints and then on the bottom it's string of?
Why does it work if this is strings of ints and this is string of int? String of int is a library function that already exists. And strings of ints is the function we're writing. So let's go back and look at map again. In fact, let's get a copy of map here. And let's get rid of the type annotations. Let's see, because we know that OCaml will infer types, even if we don't write them. So let's see what type OCaml infers for map if we don't tell it that we want to map ints to ints. So I just got rid of the type annotations there. It's the same map function as before. Let's send it down with Control-X, Control-E, and see what type it has. So what type does it have? So these are those type variables that we saw last time. We have tick A, which I'm going to pronounce alpha, and we have beta. So what this says is map takes an alpha to beta function and an alpha list and gives you back a beta list. So in fact, we can write that down. We can say map takes an alpha to beta function and an alpha list and gives you back a beta list. So that is much more general than the version of map that we wrote before. And when we say polymorphism, at least in OCaml, this is usually what we mean. That we're not restricted to one type like int, where we're able to work on multiple types. In fact, alpha can be any type, and beta can be any type, as long as we have a function that converts between those two types. So we can now say let strings of ints. I'm going to write these types down to make it really clear. int list, and we want to get back a string list. Well, what do we want to do? We want to map string of int over the list x's. So the version of map that we just wrote now lets us work on types other than int. It's polymorphic. Any questions about that? Yes?
So originally, you didn't have any types, and you had to guess what types you wanted,
Mm-hmm.
and you knew that you wanted from alpha to beta.
Mm-hmm.
I didn't know you wanted from alpha to beta and not alpha to alpha.
That's a good question. So I didn't write down any types, and like you said, I had it guess what type I wanted. Well, I didn't really have it guess what type I wanted. What I had it do is tell me the most general type that that has. So there's an algorithm which I'm going to show you in a couple weeks that looks at the code, and the reason why it told us an alpha to beta is, as opposed to alpha, is because that's more general. Because you could make alpha and beta, you could instantiate them to the same type. You could instantiate them both to int, but being able to make them different types is more general. And the whale camel's type system works when it infers types, it will always find the most general one. Yes?
So the version of map you just wrote, is that exactly like it is in the library?
No, but almost. That is not exactly like, sorry, I should keep repeating questions. This version of map is closer to what's in the library, but it's not exactly what's there in the core library that we're using. Yes?
I'm so confused. What's the difference between string of int and strings of int in terms of functions? I know you said string of int was a library versus we're writing string.
Yes. So the question is, what's the difference between string of int and strings of ints? Well, let's type them into utop and see. So string of int has type int to string. So we would use it on, say, a single int and get it back as a string. And that's a function that exists. It's already there. It's in the library. Strings of ints is the function we just wrote that takes an int list to a string list. And so to use that, we have to give it a list of ints and we get back a list of strings. Does that answer your question? Was there a question over here?
So when you're writing functions, is it better to use the most general types that you can, or to have it be as specific as you need it?
When you're writing functions, is it better to use the most general types that you can, or should you make it more specific? This is a fine question of style. I would say that making something more general is probably good because you might find other uses for it later that you hadn't thought of. There might be a few cases where the general type, like the most general type, is so big and complicated that you can't look at it and understand it. This happens, in which case you might be better off writing a more specific type. This is a hard question to answer because it's a question of style. Okay. We have 15 minutes left. Perfect. Okay. So similarly, fold can be polymorphic, and fold is going to get an interesting type. So what's an example of a function? So, the fold right that I wrote operates on lists of ints and gives you an int, but we could come up with functions with different sorts of types. For example, here's a function, keep only the positive ints in a list. Some of you might know that there's another thing for just filtering, but let's do this for now. So let's write keep positive is going to take a list of ints and return a list of ints. So we want to take a list of ints and we want to remove the ones that are not positive and just keep the positive ones. Now, the type of this looks like we could do it with map, because map lets us take a list to another list, but map doesn't let us throw things out of the list. The list that comes out of map is always the same length as the list that comes in. So we might then say we want to do this with fold right, but fold right, as we wrote it, always returns an int. It doesn't let us return other types. So how are we going to do this? Well, let's write this function first and then see if that shines some light on it. So if we get the empty list, we want to give back the empty list. And otherwise, we have the head of the list and the tail. And we want to say if x is greater than 0, then we want x and keep positive for the rest of the list. Otherwise, We just want keep positive for the rest of the list. Now, I'm going to do something a little bit funny here. You might notice that I wrote the recursion twice. That's a little bit weird. I really only have to write it once. What I could say is, let rest equals keep positive x's prime in rest. This isn't any more efficient for the computer. It might be more efficient for our reading, but it's going to make our next step clearer. Because it makes it clear that what we're doing here still is we're recurring, and then we're taking x and in some way combining it with the result of the recursion. And in this case, the way we're combining it is we're consing it on if it's positive and not if it's not positive. So we could write that function that does that, and we could try to pass it to fold right, but of course fold right doesn't have a general enough type yet. So let's generalize the type of fold right. So here's fold right, and I'm going to use the same trick I did before, which is I'm going to ask OCaml to figure out what the most general type for fold right is for me by removing these type annotations. We could also reason our way through this, but I'm not going to do that today. So we'll send the definition down there, and let's look at the type of fold right. Fold right says it takes an alpha to beta function. That's a little bit different. And a beta, and an alpha list gives back a beta. I'm just going to say A and B maybe. So looking at this, the first thing I notice is B is the result type, and A is the list. So we're taking a list of A's and somehow turning it into a B. How are we doing that? We're providing a starting B, and then we're giving a function that can take each A and combine it with a B to get the next B. Does that make sense? So if I write this up here, I can say f is an A to B function. That is, it's a function for taking one A from the list and combining it with our result to accumulate the result. Z is our initial result, and X's is the list that we want to fold, and B is our result. So let's see how we can use that to write keep positive then. So we have an int list, and we want to return an int list. So looking at this, if we're taking an int list and returning an int list, what is A going to be in this case? What kind of list are we processing? An int list. So A is going to be int. What's B going to be? B is our result type, so B is going to be int list in this case. So let's try it. We're going to fold right. Fold right needs a function. I'm going to punt on that for a moment. It needs an answer for the empty list and the list to fold. So the answer for the empty list, we can see here from keep positive, is the empty list. X is the list we want to fold. So what we have left to write is this A to B function. So that is, it's a function that takes one element of the list, and it takes the result so far, and it needs to combine them. And it needs to combine them in fact, let's call that rest. It needs to combine them in the same way that they're being combined here. If x is greater than 0, we want to cons x onto the rest, otherwise just rest. So that is to say, if x is greater than 0, then we want x cons rest, otherwise we want rest. How do I know what rest is? It's the parameter that I named right here.
How does it know that rest is the rest of the list?
Rest is not the rest of the list. It's the result of folding the rest of the list.
Oh.
And it knows that because when I wrote it, the second argument to f is recurring to fold the rest of the list. Okay. So this version of keep positive, let's try it. 2, -2, 3, -8, 7. It worked. Do we have any other questions about that? Yes, someone.
Could you briefly explain again the A to B to B section?
Yes. Could I briefly explain again the A to B to B? So this is a fairly tricky thing. In fact, it's so tricky. Have any of you heard of the Python programming language? So the designer of Python is a guy named Guido van Rossum. Python used to have a version of fold right in it called reduce, and he got rid of it. And the reason he got rid of it is he said every time he wants to use it, he needs to get out some scratch paper to work it out. So that's the designer of Python. You guys will not need scratch paper to use fold right a few days from now. And 2 weeks from now, it'll be easy and second nature. But it is complicated at first. So that's a legitimate question. So the way you should think of F is it's the operation that combines one element of the list, whose type is A, with B, which is the result of folding up the rest of the list, and gives you back the result of folding in that additional A. So F is the way of taking one element of the list of type A and combining it with the result of folding the rest of the list, which has type B, and then gives us back the result for that additional element, which also has type B.
Where would you put the parentheses if you wanted to further, like?
Where would I put the parentheses? So I would put them here.
Okay, can you explain that?
I can explain those parentheses as saying that in OCaml, arrow always parenthesizes to the right.
Okay.
If the parentheses were here, f would be a function that takes a function and gives back a b. It turns out that there aren't any functions with this type. Yes?
So, 2 questions. One is, where do you define z as 0?
Where do you define z as 0?
Yeah,
Well, z isn't always 0. So in this case, for keep positive, I'm using the empty list for z.
so z, because of the way you generalize it, doesn't necessarily have to be in.
Right. Z has to be the answer for the empty list. And so in the case of keep positive, where we're returning an int list, the result for the empty list should be the empty list.
And then also my second question, what's the difference between the first keep positive and the second?
So the difference between the first keep positive and the second is that the second was easier to write.
Okay, so is one more efficient than the other?
With a naive compiler, the first keep positive might be compiled more efficiently than the second one for reasons that I can't get into right now. With even like a moderately good compiler, they should probably turn into the same thing. All right, do we have any other questions? All right, we have one more thing to get to. Actually, 2 more things to get to. I'm going to show you a trick for how to think of fold right. Here's my trick for how to think of fold right. If you say fold right of some function and some ending value, or initial value, and some list, and suppose that list is, I don't know, A, cons, B, cons, C, cons, empty list. So that's the list ABC written out as con cells. Well, this is equal to replacing the empty list with Z and replacing each cons with F. So that is to say, this is equal to F applied to A, applied to F applied to B, applied to F, applied to C, and Z. So that's a way to sort of visually see what fold right is about. It takes your list, and if you think of it as replacing the end of it with Z and each cons with an operation, it does that. It folds it up that way. Okay. So the last thing I need to show you is the library versions of these functions because they're a little bit different. So I'm going to show you list.foldRight from the library. List.foldRight has a type with some things that we haven't seen in it before. Yes, there's a question. Explain what again? Oh, explain this picture? Explain this picture again. So what I'm saying is one way to think of the way fold right works on a list with an operation F and initial value Z is it replaces the empty list with Z, and then it takes each cons and replaces it with F. Okay. So in particular, if you fold right where the function does cons and Z is the empty list, you get a copy of the same list. All right, so this fold right in the library has a type that we haven't seen before. And what you can see here is that it takes an A list, so the order of the arguments is different from ours, and then it takes the A to B, and the B, so it has basically the same arguments as our version, except that two of them are labeled. The function is labeled F, and Z is labeled init. So if I want to use list.foldRight, what I have to do, well, it takes x's, it takes the same arguments as ours, but in a different order. So it takes x's, the function, and the empty list, but because those are labeled, you have to tell it, you just have to write the labels on the arguments there. So what you can see there is in the places where one of the arguments has a label like f colon or init colon, I pass it with tilde f colon or tilde init colon. It's just a little bit of syntax. The advantage of labels is that they let you give the arguments, they let you rearrange the order of the arguments. So, we could rearrange it like that, say, and it'll all work. So the reason they do this is so that if you want to partially apply to the first argument or the second argument or the third argument, you can do it by partially applying using the label. And it is 2:30, so thank you.